So you get both effects going on there. Magnetic force trying to narrow the beam, and the electric force trying to widen the beam. There's a fine line there as to which one is it. You really can't get it as narrow as, really, really, really narrow, which would be nice if you could. Then you'd have more chance of them running into each other. You'd have more collisions to look at. But there's both effects going on there. So that was all the equations we had back in these other chapters. Well, in the first chapter for this week, we're going to talk about what's called induction. Current is producing magnetic fields, either here or in that one. So in around 1800, 1805, somewhere in there, Ørsted, trying to show there was a difference between electricity and magnetism, sets up the experiment, runs a current through a wire, and then takes the compass needle, brings it close to it, and discovers, hey, it's not, unaffected by that current. The compass needle is affected by the Earth's magnetic field, but it's also affected by that current going through the wire, depending on which way it's going and where the compass needle is. And so he was able to show that, yes, currents do produce magnetic fields going around that current. Well, if currents can produce magnetic fields, can we use magnetic fields to produce currents? And so electricity can produce magnetism if it's moving. Can you make magnetism produce electricity? That was the thing. That was the question then. And we like symmetry. If at all possible, we like things to be symmetric. And so they started looking, and it was around 1820 to 25, somewhere in that time frame, that Michael Faraday comes along and is able to finally show us what do you have to do with magnetism in order to create electrical currents. And that is then called induction, or Faraday's law of induction. And Faraday's law of induction, you see this symbol, the letter there actually stands for abbreviation of EMF, electromotive force. It's not really a force. What it is voltage. So you're going to induce a voltage, as opposed to like hooking wires up to a battery. So that's a direct voltage that you're creating there with the battery makeup, all the chemicals in the battery. You don't need a battery, though, to create this voltage. Okay, but we still use the word EMF. We write it that way, but just think of it as a voltage. Replace it with a capital V for voltage, that's fine. Gives you the same thing. That induced voltage is proportional to the change in the magnetic flux. So they'll write it as a dV dt, where the V, magnetic flux, is the magnetic field strength times the area and times a cosine of an angle between the B and the A. We just mentioned electric flux a little bit back when we were doing Gauss's law. Electric flux, remember, that Gauss's law was that electric flux through a closed area was the integral of the E dot dA, and that was equal to the charge inside the area divided by that epsilon naught. And we really didn't do any problems with that. I showed a couple of examples, I think, with that. That was electric flux. Magnetic flux would be the same thing. I can't remember if I've still got that integral for the flux on the formula sheet or not. At least for this class, you can ignore, if I've still got it there, ignore the integration for that flux. We're not going to do that. So if it's going to be flux, it's either going to be constant or it's going to be time dependent. So that says you've got magnetic field, you've got an area, you've got a cosine of an angle between them. And again, the area vector is perpendicular to the surface. So if you've got this magnetic field lines going through space here, and I put this area here, and had the field lines going through the area. The flux is like a measurement of how many field lines are going through that area. So it's perpendicular, field lines are perpendicular to the area, well, then you got maximum flux going through there. But if the area was tilted over and they're 90 degrees to each other, so you got your area vector that way, but the flux vector is that way, then there's no flux going through the area. The area doesn't have a thickness to it. Okay. You know, geometry areas here, they're infinitely thin, got length and width, but no height. Some other angle, okay, you got a portion of it. Most problems we'll deal with, especially when we're using this for flux, it's either going to be perpendicular or it's going to be 90 degrees. Excuse me, perpendicular or parallel. And so you might have a magnetic field that's perpendicular to the area, which would be parallel to the surface, parallel to the area vector. You got maximum flux, and then maybe you rotate it, so now your B and your A are perpendicular to each other, and therefore you get zero flux. You have a change in the flux then, and then how long is that taking? That would be the dt. So that's the magnetic flux. Most of it's going to be just mathematical. Looking at it conceptually, where it's a delta phi over delta t as opposed to a d phi dt. So if it's a finite change in time, then do a delta phi over delta t. If it's an infinitesimal change in time, then it's a d phi dt. What we will tend to use this with is with coils. You got a coil, which means it's got some number of turns in the coil. And so it's directly proportional to the number of turns that this change in flux is doing. Now, there's also a negative sign here. If you're ever calculating like this voltage, ignore the negative sign. The negative sign goes by what's called Lenz's law, L-E-N-Z. And Lenz took Faraday's results here, and he said, well, what's happening is, though, this voltage is that you're inducing by this changing magnetic flux is always opposing the changing magnetic flux. It's trying to limit that change. So, and it's the mechanical equivalent of that would be like air resistance for the skydiver. The guy jumps out of the airplane, he's got gravitational acceleration downward. But what happens to that acceleration as you fall through the air? If you do not ignore air resistance. Acceleration puts a force upward over you, right? And that acceleration, actually, if you reach that, what's called a terminal velocity, the acceleration goes to zero. And now you're just falling at a constant speed toward the Earth. So that air resistance force is opposing the gravitational force that is trying to pull you toward the Earth. Now, it doesn't bring you to a stop, but it slows it down, slows down that gravitational acceleration and makes it smaller, and could eventually bring it to a zero acceleration, but you're still falling. If you ever came to a stop, the air resistance would disappear and gravity would take over again. You'd start to accelerate again. So that's the mechanical equivalent. Here, this induced voltage opposes the changing flux. It doesn't keep it from, doesn't make it a zero change. The change is still there, but it tries to slow down that change, tries to limit the change. One way to see that happening, a little harder to see what the change actually is there. Magnet go. We've got a coil. Here's our good old galvanometer. And with the galvanometer, we can measure current in either direction. With the resistance lab. So here's the galvanometer. It's on zero now, so there's no current going through this. But if I take the North Pole, and I'm going to try to do this, okay, I'm going to push the North Pole into the coil. And the galvanometer moves which direction, for those who can see it? It moves to your right. But what if I pull the North Pole out of the coil? It moves to the left. If I push the South Pole into the coil, it moves to the left. If I pull it out, it moves to the right. Now, we don't know which way this is wound. But the current being induced because of this induced voltage as I move the magnet in or out of the coil. If I move it in and out, current goes back and forth. I have a changing voltage being induced as I'm moving that magnet. And that produces then, because this is a complete circuit, it produces an induced current in my circuit. As I see that current in the galvanometer. You notice the magnet's inside the coil now, but there's no current going there because it's not changing. It's got a magnetic field inside of it, but it's not a changing magnetic field, and therefore there's no induced voltage or current being produced in my circuit. So in order to have this induced electricity, I've got to have a changing magnetic flux. Doesn't matter which way it's changing, it just has to be changing. It has to be getting bigger or smaller or something. So if I'm thinking here, so I'm taking my North Pole, it's way out here right now. There's very little flux going through this coil due to the magnet. Now, there's some due to the Earth, but it's not really changing that much. I'm not even sure that I can see this happening, but you can see a little bit. Really close. You can see that needle move slightly as I just move this toward it, not actually inside it. But I'm going from very, very little out here to a whole lot as I push it in, and therefore there's a change. Or when it's inside, I've got basically all the magnetic flux inside the coil, and I pull it out, and it goes to zero flux. So if I knew what the flux was to start with, the VA, cosine theta, and pull it all the way out to where now it's zero, I could say I've got a delta phi over delta t. And if I knew how many turns there were, I could multiply with the number of turns. So that's our basic equation for induction. Faraday's law of induction. So Michael Faraday comes up with it. He at least first published it. There's actually another scientist over here in America. Faraday was in England. A guy named Henry, and his last name, and I don't remember whether he was at Yale or Harvard, but in the 1820s, about at the same time as Faraday, at either Yale or Harvard, he made the same discovery experimentally, that how could you use magnetism to produce electricity. He didn't publish it though. Faraday did. So Faraday gets his name on the law. They discovered it after Henry died, and some of his friends were looking through a bunch of his papers, and they found all this work, and so they published for him after he posthumously there. And so later he gets his name on another quantity, because Faraday already had his name on this. But anyway, so that's Faraday's law of induction. The thing about this is you can have a changing magnetic field, which is what I was doing as I push this in or out. Change the total magnetic field inside the coil. You can make it bigger, smaller, whatever. Or you could have a changing area. Now I can't change the area of this coil. But if I could make the area bigger or smaller, that could also have a changing flux without ever changing the strength of the field itself. You just change the area. But then you could also change the angle. So here, angle would be 0. 0 or 180, one or the other. Because the area vector perpendicular to that surface, and then the magnetic field vector, so coming North Pole or South Pole, be also this way. So they're parallel, but then if I rotate the area, I'm going from parallel to 90 degrees, so I'm going from maximum flux to 0 flux, or at least the total, the biggest amount with it right like this, to 0. And then back to maximum, back to 0, back to maximum, back to 0. And I don't think I can see that happening. Oh, yeah, it does a little bit. It's just not real strong, so it's hard to see it. But yes, you can change the angle. And electric generators basically do that. They'll have a magnetic field, generally a stationary magnetic field, and then you have a coil of wire that you rotate in the magnetic field. So you mechanically rotate the coil, and then that angle, that changing angle, continually changing angle, produces a continually changing voltage, which then could produce a continually changing current in whatever your circuit is, assuming it's a complete circuit. And that gives you then alternating current. As the current goes back and forth, as that angle between them changes periodically. So that's the whole idea behind electric generators. How do you produce electric current without hooking it up to a battery of some sort? So that's Faraday's law of induction. Very important principle electrically. If you've got an alternating current going through a coil that's in a magnetic field, that can produce a force, because you've got this force acting on a current that's inside the field. Well, but the current's changing, so the force is changing, which can then actually cause a coil to start rotating. And electric motors are on that principle. This alternating current going through a coil that's in a field, and then it puts a force on it, or a torque on it, more technically, and it causes the coil to start rotating, so you're turning that electrical energy of the alternating current into mechanical energy of rotation, and that's your electric motor at that point. Whereas the electric generator takes mechanical energy, you're mechanically rotating the coil to produce electrical energy, electricity running through your wires. So we've got this. If we had a coil, and let's say it's got 100 turns, and we have a bar magnet. And let's say the strength of the bar magnet is 0.2 Tesla. That would be right at the pole. And so you got this coil, 100 turns, and hooked up here to some resistance, so you got a complete circuit. You got your bar magnet inside there, north pole, south pole, and in a time of a tenth of a second, you're going to pull this all the way out. What's going to be the induced voltage in this circuit? Well, the induced voltage then would be the number of turns. And instead of a d phi dt, since I don't have an equation to take a derivative of, it's just a change in the flux with respect to time. So I've got my 100, and the final flux, so I've got the final flux minus the initial flux over the time it takes to do that. Well, if I pulled it all the way out, final flux is going to be 0. That initial flux, when it's in here to start with, is the B times the A. But the way I've got this drawn, where the magnet is all the way inside, again, B and A are parallel to each other. So you just say times cosine of 0. Okay, so I'm going to have final minus initial. So technically 0 minus the 0.2 times, I need to give you something else here. Okay, let's make the diameter of this coil 1 centimeter. Again. So this initial V times A, initial flux, the V is pi times the 0.005 squared. 1 centimeter, 0.01 meters, so the radius half of that half of a centimeter, or 0.005 centimeters. So B times A, cosine of 0, and whatever that is mathematically. So 0.2 times pi times 0.005 squared is now 1.57 times 10 to the negative 5. May or may not ever need this unit. Unit on flux is called, it's a WB. It's the name Weber, W-B-E-R. That's the standard unit for flux, for magnetic flux. So it'd be that amount. So what's the change? And if you want to get real technical, it's minus in front there. And so that's going to give us a positive 1.57 10 to the negative 5. And divided by 0.1 seconds, which is now 1.57 times 10 to the negative 4 volts, would be the voltage induced by this magnet being pulled out of the coil. Now, so you just have that sort of a calculation. And most of these problems involving coils and just magnets, where they tell you like the magnetic field strength of the magnet, you're either starting with it all the way in and you're pulling it all the way out, or you're starting with it all the way out and you're pushing it all the way into the coil. So you're going from maximum to 0 flux, or you're going from 0 to maximum flux. And even if that voltage ends up as being negative because of the negative in front of the N, write it as a positive number. Don't worry about, is it positive or negative voltage? Just write it as a positive number. It's the magnitude of the voltage at that point. And then if you were told like what the resonant or the resistance of this coil was, or resistance of the circuit that it's hooked up to, then the voltage would equal the current times the resistance. So you say the induced current is that voltage divided by whatever the resistance is. You can make those sort of calculations. As far as that Lenz's law, that negative part, especially with coils. Let me set up a coil system here. Here's my coil. It's wound front to back, going left to right. Okay, here's my resistance to make it a complete circuit. Easier to see if you can see which way the currents are going as opposed to the voltage. If I take like a bar magnet, I'm going to take my north pole and I'm going to move the north pole into the coil from that end. Which way is the current going to go through my coil and through that resistance down here at the bottom? Which way does the current go? Well, as the north pole comes in this way, it's going to induce this voltage in the coil. And depending on how many turns I've got and how quickly I'm moving that north pole in, plus, what's the diameter of the coil, what's the strength of the magnetic field, and all of that. I don't know that, but I can't get a number, but I can tell you which direction the current's going to be. This negative sign says this induced voltage is going to oppose the changing flux. So if the flux is getting bigger going this way, I'm getting more and more field lines coming into it, then my voltage wants to produce, remember, because current going through a coil, whatever it is, gives us a magnetic field. So the voltage induces a current going through the coil. The current produces a magnetic field, but you want that magnetic field to oppose the magnetic field that's actually producing everything here as the magnet gets pushed in. So I would want the current to produce a magnetic field going the opposite direction due to this current. Well, if the field is going to the left out of that end of the coil, which way does the current have to go? Well, I'll go back to my third right-hand rule. Now here I knew the direction of the current and I figured out which end was the north pole. But if the current's going out of a end, that's the north pole, right? Magnetic field lines. Field lines go from the north around to the south. So this field being produced by this induced current is going this way, coming in that end. So this is the north pole, that's the south pole of this induced current in my coil. So I'll put my thumb in the direction of the north pole to the left. Which way are my fingers going now? Going that way, which would be front to back. So it says the induced current must be coming in this side, out on this side, and going right to left through that resistance where it's drawn. That's opposing this magnetic field going into the coil from this end. Or if the winding was the other direction. And I've got my north pole coming into it. Well, again, it wants to have a north pole to oppose it going to the left. So I want my magnetic field due to this induced current going around like that. But again, that's front to back. But now the front side is over here on the right, back side is on the left. And so the current must be going the opposite way for my resistor down there. Now that one I can actually show. I have no idea which way the winding is on this. But if I take my north pole here, take my north pole, shove it in this end of the coil, well, then move the galvanometer to the right. So presumably the current's coming in this side, coming out of that side. If I turn the coil around and push the north pole in, now it goes to the left. So it's going the opposite direction when the coil is turned the opposite way. So it goes to the left, going in, this one goes to the right when it goes in. Or excuse me, that one went to the left, and this one goes to the right. Now, what about when I'm pulling it out? So if I had this top one up here, instead of moving the north pole in, what if I'm moving this magnet away from it? Well, again, the current wants to oppose that, try to slow it down. So that's the north pole getting further away from this coil. So the coil wants to produce a north pole that's down here and a south pole on this end to try to attract that north pole back to it. And so it must be coming out of that side and coming in into that end. North pole is there, so thumb to the right, fingers are coming back to front, which means it's going this way, and then this way, and now that way. And that's what's happening when you push the north pole in, and it goes to the right, and you pull it out, and it goes to the left on this galvanometer. All of that relates to what's called Lenz's law, that negative sign in the equation. It's opposing the changing flux. If I give you those kinds of questions, a lot of it will be where you've got a drawing, something like that, especially for coils. Because then, you can use that third right-hand rule to figure out, okay, which is the north end of the coil, north pole into that induced current's magnetic field. But it's opposing. So if you got a north pole going into the coil, you want the north pole of the current to be pointing toward the north pole that's coming toward it. Or if the north pole is going away, you want the south pole pointing toward it, or vice versa. So look, and then look to see which way are your fingers going. Is it back to front, front to back, and which way does that mean the current has to be going through your coil? And if it's connected to like a resistor down there,